Okay, this is problem 5.62, and the system shown in figure 5.24 below. The mass M1 is excited by a harmonic force having a maximum volume of 50 Newton, maximum value of 50 Newton, and a frequency of 2 Hertz. Find the force amplitude of each mass for M1, which is 10 kg, M2 5 kg, K1 is 8,000 Newton per meter, and K2 2,000 Newton per meter. So from the given frequency of 2 Hertz, you can find the frequency input. Okay, you can find the omega using the formula omega equals to 2 pi f. Alright, omega equals to 2 pi f. So 2 pi f, which is the frequency now, is 2 Hertz. So you can find 4 pi radian per second. And the force amplitude is 50 Newton. Okay, remember the force is only at M1. The mass M1 is excited by the harmonic force with a value of 50 Newton. So F1 only at M. Okay? Only at M1. So as you can see here, for problem 5.62, the figure is using the same figure as your problem 5.5 before. Alright? Where in question 5.5, the values of M1, M2, K2, and also K1 are all different. But the question wants you to find, for problem 5.5, the natural frequencies and mode shapes. Okay, and they are using the same figure. Okay, figure 5.24. So for 5.26, also the same figure, right? But now we are going to find the force amplitude or the response using modal analysis. Okay, where in order for you to get the modal analysis, the steps are exactly the same. Okay, the first step, okay, the first half step is exactly the same as 5.5, where you have to, as you can see here, you have to find the equation of motion, rearrange, change to matrix, then you get a frequency equation, change the frequency equation into, solve it using determinant equals to 0, and then you get to the power of 4. Alright, as you can see here, you get the answer into the power of 4, and then you have to change it into a quadratic equation and solve the quadratic equation, and then you get omega 1 and omega 2, and then the last step is to find the mode shapes. Alright, okay, you can refer back to the previous question in your PDF, or you can watch back video for 5.5. Okay, we'll do the exact same, okay, but for modal analysis, after you find the mode shapes, you have to do some more methods after that to find the response. Okay, but now let's do for 5.62. Okay, since they have the same figure, the same system as from the previous question, so you'll have the same equation of motion. Alright, only that, as you can see, at M1 equation, alright, at X1 equation, here you have extra equals to F1 because there is a force acting at M1. Like for the previous question 5.5, the first equation equals 0 because there are no force. Okay, there are no force for this question. But for this question, there are force at M1, so we label it as F1. So from there, okay, remember, this is 2 degree of freedom. Okay, for 2 degree of freedom system, your equation of motion, you have to change your equation of motion into a matrix form, where this is your mass matrix and this is your stiffness matrix. Okay, both equations is equals to F1 and 0 respectively, so that's why we put F1 and 0 over here. Alright, so M1 is for X1 double dot, like this one. M2 is for X2 double dot, like this one. Remember, you just rearrange it into a matrix form. So that is your mass matrix. All right, next, for x1, all right, for x1, you have k1 plus k2 for the first equation and negative k2 for your second equation. So that's why we put it k1 plus k2 and also negative k2. This part here is for x1. All right, for your x2, all right, you have negative k2 and also positive k2 for the first equation and the second equation respectively. So negative k2 and also k2 for x2. All right, that's how we put it into a matrix form. And then after that, we are going to change it into a matrix. Okay, same method. Okay, we are now aiming to get the mode shapes. So after that, rearrange before you want to change to matrix. So now we rearrange it into this form. If you want to rearrange it, you rearrange it. If you don't want, then just straight away go to matrix. I just put this step by step, as simple as possible, so that you guys as detailed as possible and also simple, so you guys can follow step by step. Okay, next, once you rearrange this, okay, in terms of x1, all right, and in terms of x2 on the right side. Okay, so then remember, okay, you have to assume, you have to put this whenever you are going to change to metric. You have to put this. Okay, remember last time for problem 5.5, I didn't put this one. All right, my mistake over there. Okay, you have to put that you assume what? Okay, you assume x1. Okay, you assume x1 equals to x1 sine omega t plus phi, and x1 double dot equals to negative omega square x1 sine omega t plus phi. Same goes for x2 positions. Okay, you have to put that you assume that in your exam, because if I'm not mistaken, if you put that you assume as such, you'll get marks for this part over here. Okay, so you need to put it inside whenever you're if you are doing this question in your exam. So, and then like always, okay, like from the previous questions, once we've rearranged, then we can straight away change to matrix. Okay, like my way of teaching last time, whatever that is with x double dot, okay, you'll get negative omega square over here. X double dot, you'll get negative omega square. So m1 x1 double dot, you get negative omega square m1, k1 plus k2. This part here is for x1, yeah. So the first equation is that, and the second equation is x1 is negative k2. So this is for your x1. So this part over here is your x2. Okay, so your x2 you have for the first equation is negative k2, and your x2 for your second equation is m2 plus k. So that's why you have m2 plus k. Since m2 is attached with x double dot, so that's why x double dot becomes negative omega square. Okay, it's actually got like 2 or 3 steps more. If you want to derive, when you put this inside the matrix, then you cancel out until you get this. But you don't have to do that. You just have to put that you assume this, and then you straight away get this. Okay, easier that way. Next, after that, you want to make this thing complete, because we don't want to solve everything in terms of algebra, right? Omega, m, it's easier to have values. So since you already have values, k1 is 8,000. All right, m1 is 10 kg, k2 is 2,000, m2 is 5 kg. So just substitute the values all in here. So you'll get this. Okay, so if you guys wondering why I didn't put f, because we do have f here, right? And then suddenly inside I didn't put f, because now, okay, this f here will be used later on, okay, after we've already found the mode shapes. But now we want to focus on finding the mode shapes. Okay, in order for us to find the mode shapes, okay, as you know, same steps to find the mode shapes. Okay, the exact same steps, but we consider everything on the right side as 0, because we want to find the mode shapes only. Okay, This thing here, the f1 and also 0 will be used after we've already found the mode shapes. Okay, so now, as always, once you get this, solve using the determinant. So solve using determinant. Okay, as you can see over here, I've already write down the formula for determinant. You can use that. So you'll get this. Okay, I just simply change this in terms of determinant equals to 0. So solve the determinant, all right, where your a times d, right? So this part here, multiply, and this part here, you multiply and then minus each other with each other, then you'll get this. Okay? And then solve that by, the normal expansion for if you have brackets. So this one multiply with this one, and then negative 10 omega square times with 2000, and the next positive 10,000 times negative 5 omega square, and then positive 10,000 times 2000, and in the end you'll get this. Alright, solve everything. Okay, so over here you multiply them just now, right? Since this part here always the same thing, so you can just straight away put it as square. Okay, the same thing multiply with itself, so you get square, right? And then solve this, you get 4 times 10 to the power of 6. And then further solve this thing over here, you'll get your answer to be, okay, you'll get your answer to be 50 omega to the power of 4 minus 70,000 omega square plus 16 million equals to 0. Okay, it's okay if you guys want to put it in terms of exponent, also can. Okay, times 10 to the power of 1 also can, doesn't matter. Okay, once you solve, you get you obviously get in terms of to the power of 4, right? You get your omega to the power of 4. So remember, this is what you call as the characteristic equation. Okay, after that, change to quadratic equation because we want to solve it using quadratic, right? So okay, simply change omega to the power of 4 becomes omega square outside. Alright, the same thing, right? It's still omega to the power of 4. I just factor out the 2 so that you can get it in terms of ax squared plus bx plus c equals to 0. Alright, so you know that your a now, okay, is 50, and your b now is negative 70,000, and your c now is 16 million. Okay, that's why we change it to quadratic equation. Then you just plug your a, b, and c into your calculator. Solve quadratic equation using your calculator. Plug the a, b, and the c. Then you'll get your omega. Okay, remember, whatever that is solved by your calculator is in terms of omega square. Okay, because as you can see here, it is in terms of omega square. Alright, so whatever that is solved by a calculator is in terms of omega square. Then you want to find your omega. So bring the square to the right side, you'll get square root. Then square root of those two answers, you get 16.9614 radian per second and also 33.3513 radian per second. So as usual, after that, we are going to find the mode shapes. Alright, so you can use the method that I taught you guys in the previous questions on how to find your mode shapes, also can. Okay, same thing. Okay, so you want to find your x2, right? Because we know that our x1 is always 1. Okay, why? Refer back to your slide. It's already been written, been explained inside the slide. X1 is always equals to 1. So what we want to find is our x2. Now, I'm going to do the method that is being taught inside the slide. Okay, you can also use the method that I taught you guys from the previous question. Now I'm going to use a different one, but you'll get the same answer. Don't worry, you can use both, anything that you want. Okay, so now based on this matrix here, okay, I use that. See, the same thing from the fourth step. Then just take one line or one equation. It doesn't matter. So I took the upper equation and I take it out, as you can see here. So negative 10 omega square plus 10,000 for x1. Okay, and negative 2,000 for x2 equals to 0. Okay, then I want to find the first mode shape, I use omega 1. I want to find the second mode shape, I use omega 2. So now, using the omega 1, so I substitute omega 1 in this omega here. As you can see, I substitute omega 1 16.9614 into this omega here. Okay, so I'll get 7,123.1091. Okay, times x1 and then minus 2,000 x2. Now, as I already explained just now, x1 always 1. So substitute x1 as 1. So you can find your x2, which is 3.5616. Okay, so from there, as you guys can see, I already highlighted your mode shapes with the green color, where your x1 is now, you use 1, right? So you get your x2 as 3.5616. So your mode shape for the first mode shape is x1 over x2. So 1 and also 3.5616. That's your first mode shape. Okay, so for your second mode shape also, just use the same equation. Alright, but second mode shape uses the second omega. So use your omega 2, okay, that we got just now, which is 33.5313. So use that, substitute in here, as you guys can see here, and then after that, negative 10 omega 2 square plus 10,000. I solve this. I get negative 1,123.0921 x1. And then this part over here I didn't touch yet, so just leave it be here. And then as usual, x1 is equals to 1. So I substitute x1 as 1. Then I find the x2, which your x2 you'll get negative 0.5615. So for the second mode shape, I already have my x1 is 1 and my x2 is negative 0.5615. So put it in terms of matrix, okay, which your phi2 is actually your second mode shape. So x1 is 1 and x2 is this negative 0.5615. So from the previous question, right, as what we've already done for previous questions, we've stopped until here, right? We've already found the mode shapes and then done, because the question just asks us to find, take out the UM, okay, either using Lagrange or summation of forces and also summation of moment using the FBD, and then find the mode shapes and also the natural frequencies. That's all. So we've already found the omega and we've already found the mode shapes. Done. That's all. But now, modal analysis is we want to change from this system, which is the 2 degree of freedom, into single degree of freedom. What do I mean by that is, as you can see from our equation of motion here, as you can see, in one equation you have two coordinates, x1 and also x2. Okay, that's why it is 2 degree of freedom. So now we want to change it into single degree of freedoms, where you still have two equations, but in one equation you only have one type of coordinates. So only x1 for the first coordinate and only x2 in the second coordinate. Okay, So basically this is already coupled, as you can if you refer back to your slide, the slide already explained about the couple. So now we want to decouple the system into two single degree of freedom system, from one 2 degree of freedom system into 2 degree of freedom system. Okay, separate. We want to separate. So from coupled to uncoupled. So now we have to decouple them. Okay, so we want to decouple them, so that's why we use modal analysis. Okay, so like I've already told you just now, from the previous question, we stopped until here. We found the omega 1, omega 2, mode shape 1, mode shape 2, stop. Now the extra thing for modal analysis is we have to continue after that, where your first mode shapes and your second mode shape, we put it as one in a model matrix. Okay, we have model matrix. Okay, consists of your first mode shape. Okay, your first mode shape here, 1 and 3.5616, and also your second mode shape here, 1 and also negative 0.5615. That's how you combine those two mode shapes into one model matrix. Alright, and then next, we are going to transform x coordinates using this formula. Okay, these steps that I'm showing you guys here is the exact same steps that is already written out in your slides. Okay, so in your model analysis slide. So transform x coordinate using this. Okay, where your x equals to model matrix times eta. Okay, we want to change to eta now in order for us to decouple the 2 degree of freedom system into two single degree of freedom systems. We have to change x coordinates into eta coordinates. Alright, so x coordinates equals to model matrix times the eta coordinates. So using your EOM matrix just now from the first step, okay, if you guys wondering, I'm going to show you guys back where how do I get this? This is from the first step. See here, our EOM matrix here. This is your mass matrix, this is your stiffness matrix. It's just that I didn't substitute the values yet here, right? Alright, so for this one, the same thing, but I've already substituted all the values for M1, M2, M1 is 10 kg, M2 is 5 kg, K1 plus K2, 8,000 plus 2,000, negative K2, and also K2. And your force at M1 just now is 50. Okay, I got it from the first step, just substitute all the values. Then, okay, you guys wondering, what is this? Also from a slide, step by step already been laid out in slides, huh? So you guys can easily refer it. But if you guys don't understand, use this video instead. So, in order for us to decouple the system, we have to get our mass matrix as diagonal. What does it mean? What does it mean by diagonal matrix? Diagonal matrix is basically this. For example, you have something here. Let's say this is A, this is B, all right, and this is 0, 0. Okay, A, B, 0, and 0. So as you can see, the values in this matrix is diagonal. Alright, and other than this main diagonal line, okay, the values other that is not situated in this diagonal line is 0. So this is what we call as diagonal matrix. Okay, so basically we are doing this to get diagonal matrix for MD and for mass and also for stiffness matrix. Okay, so basically we actually our mass matrix is already diagonal, right? There are values only at the main diagonal line. Other than that, all zeros. So this is already diagonal. but we want to make everything into diagonal because our stiffness matrix is not diagonal. Okay, this is not 0, this is not 0, so that's why we are doing this. We want to get mass matrix and stiffness matrix to be diagonal diagonal matrices. So in order for us to do that, we have to post multiply and pre-multiply the post multiply with model matrix, and pre-multiply the EOM by the transpose of the model matrix. Okay, so what is transpose? If I'm not mistaken, you guys already learned this in your linear algebra class, but I'm going to show you guys in a bit on how to use that using your calculator instead, easier. Okay, so what is post multiply and pre multiply? This is post multiply, multiply after the mass matrix by the model matrix, and pre multiply used by the transpose of the model matrix. So this is your mass matrix, post multiply with the model matrix, and pre multiply by the transpose of the model matrix. Do this for both model matrix and also the stiffness matrix. Okay, and also here. But for the right side of the equation, okay, on the right side of the equation, you just have to pre-multiply with the transpose of the model matrix. Okay, so basically, as you can see here, transpose, transpose, and transpose at every matrix in your EOM, but times with the model matrix only after the mass matrix and after the stiffness matrix. So we call this part here as MD, diagonal mass matrix. We call this part here as KD, diagonal stiffness matrix, which we are going to calculate after this. Okay, so if you guys wondering why suddenly from x coordinates into eta coordinates, okay, because as I've shown before, x coordinates equals to model matrix times with the eta coordinates. So x here can be changed into eta times model matrix. So x here equals to eta times model matrix. X over here equals to eta times model matrix. All right, using this formula. Okay, next. How are we going to calculate the MD and also the KD, the diagonal mass matrix and also the diagonal stiffness matrix? So let's go for diagonal mass matrix first. This is transpose of the model matrix times the mass matrix times the model matrix only. So we know that our model matrix just now is this one, 1, 1, 3.561, and also negative 0.5615. That's our model matrix. So this is our model matrix, except that the pre-multiply, the model matrix is transposed. For the pre-multiplication is transpose of the model matrix. So you guys can use this inside. You guys do know, right, that you guys can calculate matrix using your calculator, your scientific calculator, either the blue one or the gray one or the newest one, which is the black and white color, right? So using this, what I'm about to show you now is I'm using the one that I'm calculating using the scientific calculator, using the application in my phone. So first, basically the way of doing it using your own scientific calculator is the same thing. Go to mode and then go to matrix, and then first of all add it. Okay, make sure you add it. Let's say I'm gonna choose so basically I'm gonna label first. So basically my model matrix will be matrix A, right? Matrix A, matrix A. All right, so for my mass matrix, okay, I'm going to label it as matrix B. Okay, and for my stiffness matrix, I'm going to label it as matrix C. Okay then, let's do this. So for matrix A is basically my model matrix, which is 1, 1, 3.5616 and negative 0.5615. Okay, after that, press clear and then shift, you press 4, and then you edit the second matrix. So I'm going to edit the matrix B. Make sure you are entering the matrix using the same dimension. The dimension of the matrix of the matrices that we are doing the calculation now is 2 by 2. So make sure the same dimension inside your calculator. So for matrix B is our mass matrix, which is 10, 0, 0, and also 5. All right, and then again you press clear, press shift, press 4, edit the third matrix, which is your matrix C. Okay, which is your matrix C. So your matrix C is your stiffness matrix. All right, we label here as a matrix C. So 10,000, and then negative 2,000, negative 2,000, and also 2,000. All right, and then you press clear. Now, okay, so now we are doing, let's say we do for the first one, the diagonal mass matrix. So basically the transpose, okay, the transpose of the model matrix. So you press shift, you press 4, and you go to maths, you got transpose matrix, right? So and then you press shift, you press 4 some more. Okay, you don't want to go to edit, because edit is what we want to key in the data for your matrix A, matrix B, and also matrix C. We go to names because we want to insert to calculate. So transpose of matrix A. Okay, as you can see, what is transpose actually? Transpose is they rearrange your columns and lines. Okay, as you can see here, this is your original matrix, the model matrix. So transpose of this matrix, you get as the one that you see inside the calculator, which is 1, 3.5616, and then 1 at the bottom left part, and then negative 0.5615. They rearrange it in that way. That is basically transpose. And then you multiply with matrix B, which you already key in just now, your mass matrix. You press shift, you press 4, you go to names, and then you go to matrix B, and then you multiply again with matrix A. Again, shift, put again matrix A. So as you can see here in the calculator, that transpose of matrix A multiply with matrix B multiply with matrix A, which is our model transpose of the model matrix times the mass matrix, and times it again with the original mass matrix. Sorry, the original model matrix. So you get that answer. So this, as you can see, this is the answer. Okay, it is actually supposed to get 0 and 0 here, so you get diagonal, right? But I'm going to tell you later why we didn't get diagonal, like exactly 0 here. Okay, because we didn't use the full value. What I mean by we didn't use the full value, we use the values in terms of decimals, right? And the decimal numbers are high, the number is very big, right? Like 0.5615, and there's something at the back. All right, so that's why the value is not accurate. It is actually supposed to get 0 over here. Okay, I'm going to show you later how we can get 0, like exactly 0. Okay, But now I'm gonna show you guys how I solve for the the diagonal stiffness matrix. So which we've already labeled just now, transpose of model matrix times the stiffness matrix times again with the original model matrix, which we've already defined model matrix as matrix A, and our stiffness matrix as matrix C. All right, this is transpose, right? Transpose. Okay, so as you can see here, so we just add it because we've already keyed in the data for matrix C just now, right? Which is our stiffness matrix. So just press shift, press 4, and then insert matrix C. So you get your answer now for matrix K, diagonal stiffness matrix to be this, exactly the one in the calculator. You can remember the way of doing this in the calculator is exactly the same with the with your own scientific calculator, but this one is exactly the same with the one with the gray color, and also the latest one, the black and white color. I'm not sure about the blue color, the old calculator, the old model of the scientific calculator. I'm sure you can solve matrix using that calculator, but the way of doing it inside that calculator is a bit different. Okay, so you can also solve it manually. But it will take some time because like there's a lot of matrix to be solved over here. So for me, it's easier to use your calculator if you can. So now, after you get your matrix, diagonal mass matrix, and also your diagonal stiffness matrix, so just substitute this back inside here. So you get this. Alright, so you've already solved this part here. Okay, so now substitute your diagonal stiffness matrix inside here. So you get this over here. Okay. Alright, but remember, there's one more matrix we haven't solved yet. Okay, which is a transpose of the model matrix multiply with the matrix on the right side of the equation. All right, which is the force matrix, which you have F1 at 50, and the force on the x2 coordinate you don't have any, so you put a 0, right? So you have to solve this here. Alright, so you can solve it manually or again using the calculator. I can show you inside this video. So you've already keyed in the value here, the model matrix as matrix A just now, right? So it's still in the calculator. So we can just insert a new matrix. So you go to edit and you go to matrix D, because we've already put A, B, C just now. So you can make this as your matrix D, which is change the dimension into 2 by 1. All right, so you can get 50 and also 0. Okay, so now you've already keyed in your matrix D. So now basically this is your matrix A as what you've already keyed in your calculator, transpose of that, multiply with the new matrix D. So make sure you press clear first in your calculator, and then go to shift, go to 4, go to names. Okay, matrix A. I'm sorry. You pick transpose first, and then go to shift 4, go to names. Only then you put matrix A. See, you've already transposed this. Okay, transpose the model matrix into the one as you see in the calculator. Only then you multiply with your matrix D, which is your force matrix. So calculate. Shift 4. Go to matrix D. So after you calculate, you'll get 50 and 50. Alright then. So you've already get that. So, and then you can take out, as you can see, you've already have a new EOM in eta coordinates. Okay, so you take, and as you can see, I just straight away change this because it is basically near to 0. So straight away use 0. As I told you now, there's many decimal places, so that's why you can't exactly get 0. But when you substitute, straight away put 0 because you want to show that this is diagonal now. Alright, so now how from the new EOM model, EOM equation of motion in terms of in matrix form, in eta coordinates, change it into this, okay, where 73.4249 for eta 1 double dot plus with 21,123.5891 for eta 1 equals to 50. That's for your first equation. Okay, just take out this part here. You get this. And then take out the second part here. Okay, and then you get this. Okay, this part is easy. Next, you have to find the time response for eta 1 and eta 2. How are you going to do that? At steady state response, and for the eta, n equals to sine omega t, where the formula for your n is f naught over k minus m omega square. This is actually the response for single degree of freedom, because as you can see, as I told you now, as I've told you before, why we do modal analysis, because we want to decouple them from 2 degree of freedom system into 2 single degree of freedom system. So as you can see, your equation now only have eta 1 and eta 2. So your for second equation now only have eta 2 and eta 2. Okay, so they are not coupled anymore. You've already decoupled them, so now they are uncoupled. So you can find this formula here in your slides for the single degree of freedom system. Okay, so okay, this is where we use the omega. Okay, don't be confused. Omega, we didn't use the omega 1 and omega 2 that we get just now, but we use the omega that we get from the question itself, where the frequency is 2 Hz. Then just now we calculate, right? Omega equals 2 pi times frequency, 2 pi f. So your omega is 4 pi radian per second, right? Use that input. Okay, don't use this. This is to find this is for the model analysis just now. Okay, to calculate the response, use the omega given by the question. So basically f naught over k minus m omega square, which is here sine omega t. So f naught, you know your f naught for the first equation, yeah? For the first equation, focus at the first equation. Your f is 50. Your k, okay, your k minus with your m, this is your m, times your omega, which is 4 pi from the question, and then sine omega t, sine 4 pi t. Calculate that, you get your eta 1 response to be 0.052 sine 4 pi t. Okay, next, for your eta 2 response, also the same thing. For eta 2, focus at the second equation, which is the equation for eta 2 coordinates. Force divided by the k, this is your k, minus m, this is your m, so you minus with the m, and then multiply with omega, and then sine omega t. Then calculate that, you get 0.045 sine 4 pi t. So you've already get the responses for eta 1 and also eta 2. And the last step is to substitute the eta 1 and eta 2 into the coordinate transformation equation. So as you can see, this one just now, the one that we use over here, right? We want to change x coordinate to eta coordinates, right? Use that formula back. Use that formula again. take out the matrix. So x is x1 and x2, your model matrix just now, okay, which is 1 1, 3.5616 and negative 0.5615, and also your eta coordinates, which is eta 1 and eta 2. So take this out as two equations where you know how like the normal way of solving matrix, row times column. So 1 times n1 plus 1 times sorry, not n, eta 1, 1 times eta 2. So you get this for the first equation. So for the second equation is second row times the column. So 3.5616 times eta 1 negative plus with negative 0.5615 times eta 2. So you get the equation down here. That's how you take out the response for x1 and also x2. So you've already have your eta 1 and eta 2 response, right? Here and also here. So just plug into here. So easy. So just plus for the first response, eta 1 plus eta 2. So eta 1 0.052 plus eta 2 0.0045. So you get 0.0097. At the back is the same, so you just add the numbers. So sine omega t, sine 4 pi t. Settle. For this one, you get the first response. To get the second response, this is the formula that you get from here, right? So 3.5161 times eta 1, so 3.5616 times 0.0052 minus with 0.5615 times eta 2, which is 0.0045. Settle that, you get 0.016. It's actually 0.01599 something. So only 4 decimal places, so you get 0.016 sine 4 pi t, sine omega t. So that's how you do model analysis to get the responses. Okay. So just now I told you guys on how to get the diagonal matrices for diagonal matrix mass and also diagonal matrix for stiffness to be exactly 0. This is how. All right. At this part here where you solve for the quadratic equation, you can't use your calculator because you'll get your answer to be in the term of decimals, right? So you have to use this formula right here to get this formula right here, you know, the quadratic equation formula to get in terms of this. All right. So you know that your A is 50, your B is negative 70,000, and your C is 16 million. So substitute everything in the quadratic formula. Okay. And then you get this. Okay, simplify that and you get this. So your omega 1 will be the minus 1. You just change this part right here, right? And then once you calculate this using your calculator, okay, normally your scientific calculator will straight away give you the simplest, simplest form of your answer. Okay, we call this as the set, right? So the calculator will give you in terms of set. All right, so as using this, you will use the entire value, all right, to calculate further on in the model analysis method. Okay, so you will not be losing any decimal places at all. Okay, so for that, okay, I'm just going to show you how. Mod maths. All right, so let's say if you calculate this, all right, so 7 exponent 4 minus 17 exponent 8 over 100, right? So you'll get this, right, in terms of decimal. So if since we don't want decimal, so just press the SD here on top of the delete button. So we'll straight away give you in terms of set, which is this negative 100 square root 17 minus 7. So you will not be losing any decimal places at all. So you'll be using the entire value to calculate in the calculations. So then, if as usual you want omega, so this is omega square, so bring square on the right side, you get square root. So then again, same thing, so I just use the entire value, not the decimal places. Everything's the same as what I've shown before. Okay, so I get my model matrix to be this. X1 is 1 and X2 is in terms of set. This is my model matrix now. Okay, go, everything the same thing. Okay, here the transpose times the model times the mass matrix times the original model matrix. So this is what I want to show you guys. Okay, if we use the entire value, not the one that have lots of decimal places, so to matrix, so I edit again the matrix A. We used the transpose just now is for matrix A, right? The matrix A for the model matrix, right? So which is 1 1. Okay, here instead of using this, I use the exact value here, which is square root 17 plus 3 over 2 and negative square root 17 plus 3 over 2. Okay, everything's the same, right? We haven't touched yet our matrix B. Our matrix B is still this one, and this is still our matrix C. Okay, in the calculator. So this is matrix A, transpose, matrix B, and also matrix C. Sorry, matrix A, original matrix A. So this is matrix A, transpose. This is matrix C just now, right? We haven't touched anything yet in the calculator. So this is the original matrix A, the original model matrix. So calculate that. So put here shift 4 mass transposed of the matrix A. Okay, calculate with times with the matrix B. Our matrix B is still the same thing. Okay, unless you clear your calculator, then the value will be gone lah. So shift 4 matrix B times with the matrix A again, the original matrix A. So now, as you can see, instead of getting 0.0008 like just now, we'll get exactly 0. Okay, because we use the entire value. No decimal places is we didn't lose any decimal points at all. Okay, during the calculation, because we use the entire value. Okay, so this is what I meant. All right, so you do the same thing for the stiffness matrix, you'll get the exact 0 also. Okay, but don't worry. Okay, whether you use this in terms of set or in terms of decimal places, you'll still get the same value. All right, that's how you do the full entire explanation on how to do modal analysis.